Hello. This is another problem on the calculation of electric flux. So the problem says we have a very long thread placed along the axis of a circle of radius r. Consider that as a ring of radius r. The charge per unit length is given. Okay. So how do we calculate the electric flux? Electric flux, we take the electric field at each point and then take a dot product of the area. So we want the area perpendicular to the electric field, or as a vector it should be along the electric field, and then you integrate it. Okay, so for us to compute the flux we need to first get the electric field. So let's take a diagram of the situation. Okay, so C is the center of this circle, and let the thread be along x-axis. Okay, so first let us calculate electric field at a particular point, let's say anywhere in the plane of the ring. Okay, so since we need anyway the electric field, I'm just considering a ring of radius r. Okay, so this is a ring of radius r, and at this point I'm trying to calculate the electric field. Okay, another thing that we need to understand is, so if I take a point P in the plane of the circle and calculate the electric field at that particular point, I need electric field which is perpendicular to the area. Okay, so I need only the electric field which points either to the left or to the right. But if I consider that the charge is positive, then I'm looking at the electric field pointing to the left. So any electric field vector which is in the plane of the ring, I can ignore it. Okay, so here again, that diagram I think we need to understand. Here I'm assuming that the circle of radius r is perpendicular to the board. Okay, and the wire is in the plane of the board. So half of the ring is on the other side of the board, so half of it is let's say facing us. So maybe I'll make few changes so that we understand. Okay, so what I have done is, like, half of the ring I converted that into dotted curve. So the dotted curve is, you can imagine that it is on the other side of the board, and the solid curves are, let's say, on this side of the board, and the wire is in the plane of the board. Okay. Okay, so at this point, let us first calculate the electric field due to the charge on the thread. So in order to do that, we will have to take a sample charge at a position x on the thread. So let's say the length of this thread is dx. So what will be the charge of this, let's say, small portion dq? So this will be lambda into dx. Now, dx is assumed to be so small that you can treat it as a point charge. So once you treat it as a point charge, the electric field at point P will be along this line. Okay. So the electric field due to this sample charge is in this direction. Okay, so let's say that is d. Okay. Now let us take let's say this angle as theta. Okay, and then if I take a vertical line here, I think this angle will also be theta. Now I'm not interested in the components which are in the plane of this ring. Okay, I'm only interested in components which are perpendicular to the ring. So what would I do? I'll just take a x component. Okay, so let's say this will be dE sine theta. Okay, so I'm only interested in dE sine theta. But I need to first get dE and then take a component dE sine theta. Okay, and if I, let's say, integrate that, I will be getting the electric field due to the entire thread at that location point P. Okay, so here let me write this. So the electric field at P, I'll put, let's say, X. Okay, so this is electric field, magnitude of electric field, okay, along x-axis due to entire line charge. Okay, so due to the entire line charge. Okay, so due to the charged thread. Okay, so what are we doing again? So we take dE and then take sine theta and then integrate it. Okay, again, keep in mind we are still able to get only electric field at a particular point after this integral. Okay, so we still have to take a step from there in order to calculate the flux. Okay, so now let us evaluate this. Okay, so EPX. Okay, so what is dE? dE is 1 by 4 pi epsilon naught. Okay, so charge of that small piece that we have taken from the thread, which is lambda into dx. Okay, so divided by, so the distance between the field point where we are trying to get the electric field and the point charge here. So let's say this is, let's take it as, okay, so I cannot take it as x. So let's write in terms of r. Okay, I think this distance will be r by cos theta. R by cos theta, yeah. So this is theta. So this will be r by cos theta. So we can write this is r by cos theta. So that is the distance between point P and the point charge on the thread. So let's put that here, r by cos theta. And then don't forget this sine theta. Okay, now there are two variables here. X is changing and theta is changing. So let's say, let us try convert everything into one variable. Okay, so I'm selecting theta here. So how can I convert x into theta? So if you take this triangle here, you can see that x by r is tan theta. So x is r tan theta. So if I take a derivative here, dx by d theta is going to be r secant square theta. Okay, so I can substitute this here. So let's pull constants out. I think I forgot something. Okay, so I'm supposed to square here, right? So distance square, yeah. So let's pull constants out. So lambda by 4 pi epsilon naught, and even r square is a constant. So let me pull that out. So inside the integral, I have cos square theta. Okay, so this flips over, and then dx is going to be r secant square theta. And then because I'm writing dx, I'll have to multiply this with d theta. I will write it towards the end. Okay, so sine theta d theta. Okay, so cos square theta multiplied secant square theta, so that becomes 1. Okay, so this r I can take it outside. Okay, so what is the electric field at that point? I'm x component of the electric field. So electric field along x-axis is lambda by 4 pi epsilon naught r. Okay, so one more r comes out. So I'm, let's say, taking only one r in the denominator. I have sine theta d theta. Okay, so I have to integrate sine theta and d theta. So what will be my limits of integration? So let's think about it. Okay, so what will be my limits of integration? My first piece of the thread starts from here, and the last piece is somewhere along the x-axis at infinity. Okay, so when I, let's say, take this line. Okay, so let's say if I consider this is an arrow, this arrow makes an angle 0 with the vertical when I'm considering the first piece of the thread. Now as I move to the last piece of the thread somewhere at infinity on x-axis, this arrow is making an angle with the vertical which is continuously increasing. Okay, so if I'm like pointing to a very far off place, I can say that this arrow almost becomes parallel to x-axis. So with the vertical, it is going to make an angle of 90 degrees. So I will have to integrate from 0 to 90 degrees, which I'll write it as pi by 2. Okay, so then what do we have? I have lambda by 4 pi epsilon naught r. Integral sine theta is minus cos theta, and then we substitute limits pi by 2 to 0. So if I substitute pi by 2, I'll get 0, and then if I substitute 0, I'll get 1, but I need to subtract. So the magnitude of electric field at point P perpendicular to the area of the circle is simply lambda by 4 pi epsilon naught r. Now we're going to use this to calculate the flux through the wire. Now let us understand one more thing here. Okay, we have calculated only at a particular point. Now think about this. If you take any point on that blue ring, okay, so take any point on that blue ring. If you calculate the electric field at any point on the blue ring and take a horizontal component of that electric field, you will still get the same magnitude of electric field that we have just obtained, right? So for example, suppose I take this lowermost part of the blue ring, okay, and if I calculate the electric field there, so this point charge is going to provide electric field in this direction, which is dE. So by symmetry, I can say that this dE and this dE will be same. And then I am interested only in the horizontal components. So this will also end up being dE cos theta. Okay, so I hope you get the point, right? So if I'm worried about only the horizontal component, any point on the ring is symmetrical to the charged thread. So at all points on that blue ring, I will have the same magnitude of electric field along x-axis, and that's what we want. Okay, now through the sample ring, if I want to get the flux through the sample ring, I need to multiply by area of that ring. So okay, so how does our sample area look like? So suppose if I am, let's say I'll do one thing here. So suppose if I am looking along the negative x direction. Okay, so if I look along the negative x direction, okay guys, so again let's visualize this. Okay, I want you to look along the negative x direction. So when we look along the negative x direction, we look at a ring like this, right? So the negative x-axis is into the board. Okay, so it is into the board. And this is the blue ring that we're talking about of radius r, and this is capital R. Now the thickness of the ring is dr. Okay, so thickness is dr. Now how do I get the area of the sample ring? So area of the sample ring dA will be, so you can just take a pair of scissors and then cut this ring and then spread it out. Okay, so if you take a pair of scissors and then cut it and then spread it, it will be like a belt, right? So the length of the belt is the circumference of that ring and the thickness is dr. So the length is circumference, so it will be 2 pi r. So it is almost like a rectangle. So we can write the area as 2 pi r dr. Okay, and we have just discussed that at all points on that ring, the electric field is along negative x direction. So in this diagram, the electric field is pointing into the board, and then we should not have any trouble getting the flux through the sample ring. Okay, so through the sample ring, sorry, through the sample ring, the flux, we will write it as d phi, will be simply this electric field, whatever we got, okay, multiplied by area. So we are taking the electric field and then multiply by area. Now if I want the overall flux, I will have to integrate this, right? So if I want the overall flux, I will have to integrate from 0 to capital R, right? So the flux will be, so let's substitute the values. So I have lambda by 4 pi epsilon naught R, and then dA, which is 2 pi R dr. Okay, then you integrate from 0 to capital R. Okay, now I think the integral looks really nice. So let's take, think 2 pi, the 2 disappears. So constants are lambda by 2 epsilon naught, they come out. And then you are left with only integral dr, 0 to R. So what will this become? I think this is simply R. So the flux will be lambda R by 2 epsilon naught.